All right, well, I guess we spent too much time in the backstage room. So anyway, hi everyone, my name's Theo. I am a PhD student, well, I guess for the next few weeks at MIT and a research partner at Bain Capital's crypto fund. This is work on multidimensional fees. So how do you do essentially congestion pricing for non-fungible resources that are contested in some way, and joint work with Guillermo, Alex, Tarun, and CMAC. So one thing that I hope to convince you of is that fee markets with fixed relative prices are inefficient. And this talk is a framework to optimally set multidimensional fees for congestion control. So let's give kind of a very brief example of why are transactions so expensive. Let's consider like a very simple example where we have a mempool and say we have a bunch of transactions and we have kind of two types of resources, so maybe compute and bandwidth. You could also think of maybe the first set of transactions, the blue ones, looks at like one account, so it accesses one particular smart contract, say in like kind of a Solana type VM, and the other accesses another. And these two things are orthogonal. And let's say, you know, the blue transactions are more valuable to the users, so they have a utility of 4, whereas the bandwidth transactions, the orange transactions, are less valuable. Well, if we have a 1D gas market and say the gas cost is 3, what would we do? We would fill up the CPU transactions, but we would actually not really use the bandwidth that we could of the validators. However, if we have a 2D gas market and say we were able to price CPUs still at 3, but we were able to price bandwidth less at like 1, we would end up filling up this block. And when I say filling up the block, this isn't necessarily in the block space context. This is more of like filling up the ability for the validators to actually execute these transactions. And this very simple stylized example illustrates why orthogonal resources should be priced separately. So what do I actually mean when I say a resource? Well, a resource is really anything that could be metered. So this could be something like blobs. It could be compute memory and storage. We could even go down to the level of individual opcodes. In fact, we could even say sequences of opcodes. So for instance, if you hit a storage slot and then you hit that storage slot again, maybe that's less expensive than hitting the storage slot and then hitting a different storage slot. We could also say compute on a specific core. We could say things like each account and an account-based model is an individual resource, and so on. So this is a very general framework that as long as I can say how much of something I used, I can call that a resource. So we're going to formalize this. A transaction J is going to consume a vector of resources, AJ, and we're going to say there's M different resources. So that means the ith entry of this vector is going to say how much of resource I is consumed by transaction J. Then a vector X is going to record which of n possible transactions are included in the block. So just simply xj is 1 if transaction J is included, and it's 0 otherwise. We can then write the quantity of resources consumed by a block. And when I say block, I mean just some unit of kind of time as this vector y, which is just going to be the sum of each of the vectors of resource consumption times this 0, 1 variable that says whether it's included or not. And we can write this simply as this matrix A, where the columns correspond to the transactions, times the vector x. So then we know most systems constrain and charge for each resource that's used. So as an example, we might define a resource consumption target that we'll call B star. And so the deviation from that target is just AX, which is the quantity of resources used by the last block, minus B star, which is our target. So in kind of the 1D gas market on Ethereum, this is going to be, you know, 15 million gas as an example. So this is in like 1559. We also might have resource consumption limits. So this says like there's some maximum size for a particular block. And that means that no block can have resource consumption, AX, that is greater than B, where B is the limit. And so finally, for each of these things, we want to charge for the amount of resources that's used. So we'll define a price vector P, and P is going to be an M vector that just says what the price is for each particular resource. So that means for a particular transaction, we can write the cost of said transaction as just P transpose times AJ. So how do we determine these prices? Well, there's a few properties that are like pretty obvious that we want. Let's say if we're consuming, if the last block had resource consumption exactly equal to the target, that probably means we set the price well. So we don't want to actually change that price. On the other hand, if we're over target, so if we're consuming too much of that resource, the network probably wants to increase the price. It means it's undercharging in some sense. And vice versa. If the consumption is under that target, then we probably want to decrease that price. So one proposal that's been given for like a multidimensional fee market, kind of multidimensional version of 4844, is this exponential rule. And if you check, you can kind of go through this, and it does satisfy all these properties. But there are actually many other rules that satisfy all these properties as well. And that begs the question, is this a good update rule? And what does good even mean in this sense? So it satisfies these properties, but what other properties might we want? What type of dynamic behavior do we want? And in the rest of this talk, we're going to see that update rules are implicitly solving an optimization problem. And so a specific choice of an objective function by the network designer is going to give a specific update rule. So instead of actually focusing on what the update rule itself should be, we're going to instead focus on what optimization problem we want to solve, and then use that to back into a specific update rule. Okay, so let's look at the resource allocation problem, which is this optimization problem. The setting for now is we're going to have an omniscient network designer who's going to be able to pack the blocks themselves. Of course, this is stylized, but we'll see that if you set prices correctly, then in effect, we're doing this in a decentralized way. So the first ingredient we need is some type of loss function. So this says, given a particular resource usage of like the last block, how unhappy am I with it? And just as a few very simple examples, we might say if we're exactly on target, we're not unhappy at all, so we incur 0 loss. However, if we're deviate from target at all, we're infinitely unhappy. On the other hand, we might say we actually don't care if we're under target, but we only care if we're above target. So if we're under target, we incur 0 loss, but if we're above target, then we're quite unhappy. The next ingredient we need is to encode all transaction constraints in the set S. So the set S is just going to say these are the types of allowable transactions we have. And this will include everything like network constraints, but it also can include very complicated interactions among the transactions. So for example, if you have some like DEX arbitrage opportunity that's at the top of the block that only one person can actually realize, that would be included in the set S as well. The final thing is we need some notion of utility that's obtained from each included transaction. So here I'm going to clump essentially everybody that interacts with the blockchain into one group, and then the blockchain itself or the network into another group. So when I say transaction producers, I mean users, validators, block builders, kind of all of this. So payments between this group, I'm not going to worry about, and I'm only going to worry about the net utility from kind of getting a particular transaction on chain. And if transaction J is included, I'm just going to say then this group gets a joint utility QJ. And of course, we almost never know this in practice, but we'll see that we actually don't need to know this as the network. So the resource allocation problem with all these ingredients is then just to maximize the utility of included transactions minus the loss that's incurred by the network, subject to the resource usage of the network is given by that of the included transactions, and the set of included transactions is allowable. So it satisfies kind of all the constraints that we have. And of course, this set S might be very complicated, but we're going to see we're able to actually outsource that, outsource the kind of complexity of that to the block builders. So as I mentioned earlier, the network designer doesn't actually solve this in practice at all. The network designer doesn't decide which transactions are in the block. The network designer doesn't know the utilities. And because of this, we're going to then lean on duality theory to set prices so that this problem is solved optimally on average and prove that this is indeed the case. So just to give a very brief outline of what duality theory is, it's kind of this deep theory in convex optimization that says essentially if we relax the constraints to penalties and we set the penalties correctly, then we solve the original problem if we set those like penalty prices correctly. And one key observation here is the network designer really only cares about the utilization, Y, so the resource utilization, based on the transactions. But they don't actually care about the transactions, or they only care about the transactions insofar as it affects the utilization. Similarly, people that are building blocks don't actually care about the resource utilization of the network, except insofar as it tells them which transactions are actually allowed to be put in. So we're going to decouple the utilization of the network and that of the transaction producers. And as I said, if we correctly set the penalty, which is going to be the prices, then the dual problem is going to be equal to the original problem, and the utilizations are going to be equal. So the dual problem is, instead of that maximization problem that we saw earlier, it's going to be a minimization problem of this particular thing called a dual function given by g of p. From before, the prices p are essentially the penalty for violating that constraint, which are exactly the prices that we're going to want to charge for each resource. So this is kind of looks very complicated at first, but this is the form of the dual function. The first term is actually something that's quite easy, and we know this in closed form for many loss functions. So I would just think of that first term as something that's easy to evaluate. This can be done on chain. This could be done as part of consensus. Typically, it's a closed form solution. This is just the general case where we don't necessarily know what the loss function L is. The second term is actually a little bit more complicated. So let's look at it for a second. Well, the second term is saying choose the transactions choose the transactions X that are in S that maximize the net utility. So the utility minus the prices that are paid for including that transaction, subject to those constraints given by S. And this is actually the exact problem solved by block producers in determining what kind of transactions are actually included on chain. So what does this mean? The network doesn't have to solve this problem. The network can actually observe the optimal solution to this problem by just looking at what was included in the previous block. So what do we get at optimality? So let's assume for a second that we set prices correctly. So we set prices correctly. We give these prices to block producers. They tell us what transactions to include. At optimality, the supply, which is essentially how much of each resource the network is willing to give at a particular price, is exactly equal to the demand. So if we set prices correctly, essentially the gradient of that dual function, which is y star, which is the solution to kind of that first subproblem, minus a times x star, which is the resource consumption of the included transactions, is equal to 0. And just taking this one step further, if we're kind of plug things in, what this means is that the optimal prices charge the transaction producers, so the people including transactions on the blockchain, exactly the marginal costs faced by the network. And these prices are those that incentivize transaction producers to include transactions that maximize the welfare generated, which is that utility term, so essentially the utility of the included transactions minus the loss incurred by the network. So that's great, but this assumes that we set the prices correctly. So the question is, well, how do we find those prices that minimize the dual function? And we can compute the gradient of this. So y star is that kind of easy term that we can compute on chain. A times x star here is just going to be the resource consumption of the transactions that were actually included in the previous block. And this means that we can essentially, determine y star, observe x star, and then apply our favorite first-order optimization technique. So for example, we can apply gradient descent. And we can kind of do this as for each block. So the question is like, well, does this work? Does this give us what I want? Or does this give us what we want? Because now we've kind of switched from this offline problem. I was like, this is a single block problem. But in reality, these systems are dynamic. So the transactions that are submitted are going to differ for each block, and so on. So what types of guarantees can we get in this scenario? And just to outline kind of what we have is we have this game that's being played essentially between the network and those that are submitting transactions. So at a particular block, which we'll index by t, first the network is going to publish some prices. So it's going to say, okay, the prices for this block are going to be pt. After it publishes the prices, then the users are going to submit the transactions. So these transactions have some utility and have some resource consumption. This might be adversarial. We're not going to make any assumptions on what transactions are actually submitted. then the network is going to receive a payoff. So after these transactions are submitted, the network receives essentially some loss, which is given by that dual function. And the question is this a good thing to do? Like, is this something that makes sense? And to do that, we're going to use this metric called regret, which comes from the online learning literature. And so what this essentially says is compare these two scenarios. In the first scenario, I'm running this gradient descent type algorithm. So essentially the algorithm that I gave you a few slides ago, that's dynamic. So you can think of this as like a 4844, 1559 like mechanism. In the second scenario, I actually have an oracle that tells me all the transactions that are submitted in the future. So in some sense, like I'm omniscient. But I have to actually, instead of being able to change the price, I have to choose the best fixed price, knowing all those transactions in the future. For anybody that's done machine learning, you can think of this as like an online learning setting where the data is streaming in, and I kind of adjust my weights as the data is streaming in and make predictions, versus this case that's like a supervised learning problem where I have all the data in advance and I have to choose one set of weights. And of course, we never know P star in practice, but this seems like a reasonable baseline, this online dynamic approach versus this offline static approach where we actually know the entire future. So the main result, and why we say that these types of fee mechanisms are optimal, is that assuming we use gradient descent with kind of a particular step size that's chosen well, we get this bound on regret. So we essentially get that regret is O of 1 over the square root of t, which means that this goes to 0 as t, which is, you can think of kind of as like an epoch, gets large. Very importantly, this result doesn't actually require any notion of like stochastic demand, any notion of playing to an equilibrium. There's no assumption on what the transactions that are going to be submitted are, except for the fact that they are valid, so they pass consensus. This means that these can be entirely adversarial, and I think in blockchain settings, like having these adversarial bounds are quite important. And these results essentially follow directly from online convex optimization, which I do think shines in this setting. As an interesting aside, this actually doesn't require that we ever converge to any prices. So it doesn't require that we converge to the optimal, and we still get this bound, which is quite cool. So again, when I say optimality, this scheme is optimal in the sense that it's 0 regret on average. And another point is there actually exists the stochastic adversary that does match this bound. So you can have an adversary that does cause you to hit this bound, so you can't hope to do better without additional assumptions. However, if you do have additional assumptions, like for instance, demand or transactions are drawn from some distribution, you will get all the nice things of like this converging to a clearing price and so on. Another thing is a lot of these online convex optimization results are stronger than the traditional game theoretic results in that they don't require things like playing to an equilibrium. They don't require a rational adversary. They only require an adversary to be bounded in a certain sense. And this could be either a bounded budget, or typically in these systems, we have some max block size. So just to go through simple examples and kind of go all the way from the loss function to what an update rule would look like. If we take this kind of silly loss function, this zero infinity loss function we saw earlier, we get this update rule that looks like pretty vanilla gradient descent. So we update the prices based on a term that looks like the residual. So B star, remember, is the target, and A times X star is the resource utilization of the last block. If we look instead at this loss function, but actually with mirror descent. So mirror descent adds an additional kind of regularization that tells us what we want the dynamics of gradient descent to look like. We actually recover exactly the 4844 update rule. And unfortunately, I don't have time to get into this, but I will refer you to the paper and happy to answer questions on this. And let's look at the other loss function that we looked at earlier. So this loss function says we actually don't care if we're underutilizing the network. We only care if we're overutilizing it. And here we get the same as we have up top, but with the differences, we don't allow negative prices. So up top, where we actually care if we're underutilizing the network, we might have negative prices, which you can think of like a subsidy. Whereas in the bottom, this loss function says we don't care if we're underutilizing things, so there's no reason that we would ever give a subsidy for someone to use a particular resource. And just to kind of wrap up, I hope I convinced you that really when designing these fee mechanisms, you should choose your objective function and the update rule, so kind of the algorithm that you're using, instead of trying to choose the price rule directly. And if you choose this objective function using this framework, you'll get kind of an optimal price update rule that has those strong adversarial guarantees. Of course, there's no difference between kind of correctly choosing these prices with an oracle that tells you what the future is, and then using these online gradient algorithms, and that's what we mean when we say they're optimal, that these things are zero regret as the time window gets large, and these results hold without kind of any assumptions on, distributions of demand or stochasticity or so on. So all these things are adversarial bounds. There's a lot of I think this area is really interesting. There are a lot of other fee mechanisms that might kind of benefit from this type of online optimization approach. Some big questions here are what should these resources actually be? I imagine this depends a lot on what type of blockchain system or rollup you have. So in an account-based model, you might want to price things per account. In other models, you might want to separate things like compute, memory, and storage, and so on. There's a few teams like Avalanche and Penumbra in particular that have been implementing these. And so, kind of these things going into real-world systems might give some insights as to how to think about this question. In addition, I gave you some update rules using gradient descent. I also gave you one using mirror descent, which gave us 4844. There's a question of what update rules are the most useful, and how do we trade off things like convergence behavior, complexity, and kind of the dynamics that we actually want for these, which might lead to different user experiences. And as I mentioned, this might be relevant for many similar fee type mechanisms. So while I'm talking about fee mechanisms on an L1 or L2, you can imagine there's a lot of protocols where you have some resources and you want to do congestion control, and you can use fees to set or you can use this framework to set fees appropriately towards that objective. Anyway, for more info, check out this paper or feel free to reach out. Thank you.
Thank you, Theo. Thanks for the nice talk. Do we have any questions? Do you mind going to the microphone, please?
Hello. Awesome. Thank you for the talk, by the way. Just a quick question I had was, well, two-sided in that, is the loss function different for both, for the dual problem for proposers, block builders and the kind of the omniscient network designer, and then with proposals to kind of decentralize the proposer process such that MEV or other adversarial forms of value extraction are decentralized, does the loss function become more optimal in the sense that the bounds are achieved in a much stronger, easier sense?
Yeah, great question. So for the first, I would say so the loss function that's in kind of the original problem, which is this problem that we want to solve, is what shows up in the dual. So it's not, you're getting kind of a different form in the dual, but the dual mechanically is derived from the original problem. So there's no I guess, room for choices when deriving the dual problem. You're essentially applying this mechanical method that spits this out from the original problem. And then for the second question, we kind of play a sleight of hand here where we're actually not, so most of what goes on between, say, the users, searchers, block builders, and validators, we group all of that together. So for example, if I'm a searcher and I have an MEV opportunity, I might pay some block builder a large amount of money to include that, and then that ends up going to the validator. And for our utility, we essentially just net out those payments. So we're looking at everybody that interacts with the network and then the network itself. And so there's a ton of research questions as to how do you get people to, right, we have this block building problem, and in this block building problem, we're saying we're assuming that people kind of submit the highest net utility transactions, but what is that actual utility? I don't know. How does it net out between these players? I don't know. How do you do this so it's make these incentive compatible between those players? There's a lot of people that have done a lot, of interesting work on that. What I'm talking about here is like once you kind of have people, like the final person that's submitting the transaction to the network, how do you kind of do congestion control? So I'd think of this more as like an inclusion, talking about inclusion rather than ordering.
Awesome. Okay. Thank you so much.
Yep.
Anyone else? Okay, I also had a question actually. That's kind of related. So, in the resource costs, you modeled it as being linear, like A times X, right?
Yes.
Is it possible that the order of inclusion in a block would affect like how much resource gets used, and like is there a possibility to extend this to nonlinear models?
Oh yeah, definitely. So actually, the what you'd end up doing with that let's go back, but the idea is essentially you duplicate the transaction. So let's say like you have a transaction, and if it's the first in the block, it's the first thing to hit a particular slot. So that kind of storage read is more expensive. Whereas if it's the second to nth thing in the block, it's less expensive to do that S read. And what you'd end up doing is you'd actually put two transactions in. So you'd have one transaction that has the resource that's like the first read, the other transaction that has a resource that's the second read. And in the set S of allowable transactions, you'd have a disjunctive constraint that says only the first one or the second one is in. And so that nonlinearity you'd basically do by duplicating it. And the reason this doesn't require like a blow up in complexity is the AX term is just, you only need to care about what was actually included. So in some sense, any transaction where X is 0, when you're computing like, Y is equal to A times X, you just throw out and you totally ignore. Does that answer the question? It's a nice modeling trick.
Can you speak a bit more about the Avalanche and Penumbra implementations of this and what you found value there?
And sorry, what?
What you found is valuable or interesting in that implementation?
Yeah, I would encourage you to talk to the teams, which I think are both, there are folks from both teams around here. But I think it's like, one thing, like I said, kind of the selection of resources matters quite a bit. And so like one thing that's kind of interesting is Penumbra, for instance, does a lot of client-side proving. So they separate out kind of bandwidth cost into what's actually like people that are running the validators have to do and what the client-side proving has to do. Let me just... So I think it's like this kind of resource selection of like how, when I say like orthogonal resources should be priced separately, nothing is truly like 100% orthogonal for the most part. And so how do you actually choose these things? And I think that's kind of one of the things that for both like Avalanche went also towards, I don't remember, I think they used 5 resources, but it was kind of like bandwidth, compute, memory, and so on. So similar to kind of the example that I had. And then there's also a lot of kind of questions of, implementation details that interact with this framework that I think are valuable to when rubber meets the road in some sense. So I think that resource selection, and then also like, for instance, do you have caps on how, or do you have things like different resources might be priced where, say, the gradient step could be faster or slower. So perhaps for some resources, you can have like huge bursty spikes, and so you actually are fine raising the price slowly, but for other resources, if you have a burst, that can't be sustained, so you actually want to push the price up quite a bit faster. And then the ability to actually like see this in practice and then on a test net, I think is super valuable for figuring out like what types of algorithms you should actually design. Then the other thing that I think is interesting on the implementation side is so Avalanche and Penumbra went more for kind of this like bucketing, I would say like bucketing the opcodes and saying like these opcodes correspond to these types of things. I'm butchering this, but for the sake of kind of stylized, like, these types of actions consume compute and these types of actions consume bandwidth and so on. Another place where you could apply this framework as well is saying, okay, I want to price each account separately. So saying like a Solana model, where you might instead say like each actually account or each piece of state has its own controller. And so I want to make things like, say if there's a big meme coin craze and people are spamming the network with those types of transactions, I want to raise the price on accessing those dexes, but I don't actually want it to be influenced by, say, other things that are using like compute. I want, say, like certain transfers to still be super cheap or accessing other applications to be really cheap. So that's another thing that, as far as I know, isn't implemented by anybody yet, but it's been talked about. And I think that's also like a super interesting path to see kind of, that wasn't the original thought when we did this research, but kind of everything applies one-to-one.
Thank you so much, Theo. Let's please thank the speaker.